Hi, today we will be finding the maximum angular frequency a cylindrical cup with some radius r and height h can have without the fluid inside the cylindrical cup spilling over. So let's get an idea of what this situation is going to look like. So first we'll have our cylindrical cup, and there's going to be some fluid sitting in it, some height. And so this height is the same value as this radius, this height of the fluid initially. So I will label this as R and this as R. And then the height of the cup I will label with H. And so what we're doing is giving it some angular frequency, and what will happen is the fluid will move in a parabolic shape up the edges of the cup. So what that'll look like is this. And so this is without the fluid spilling over. So what maximum angular frequency can we have without this fluid spilling over the edge of the cup? This is still H, but now the fluid has dipped and moved upwards. And so in order to find this angular frequency, which is labeled it with omega, we're first going to need to find an equation that solves for height at whatever radial coordinate you're at. So say this coordinate, small r, what is this height of h sub r? What would that height be at this radius with some certain angular frequency? So what happens here is we have these two equations. The derivative of pressure with respect to position is equal to the density times the angular frequency squared times r, some position. And then the pressure is equal to density times the acceleration due to gravity times some position of h. So first what we're going to do is write down that first equation. dp dr equals rho omega squared r. So we have here is some separable differential equation where we'll solve for pressure, and then once we have pressure we will sub this equation back in and then solve for h. So here, move over, we'll have the integral bounds from 0 to p, dp equals, and then what happens is you move this dr over, and these are constants with respect to r, so we can pull that out of the integral. Rho omega squared integral from 0 to r. And this is, we'll have these as dummy variables of integration. So we'll put r prime, dr prime. And so then when we solve this, we get p equals rho omega squared, and then r. Well, r squared over 2. And so, like we said earlier, we're going to now sub this equation back in for pressure and then solve for height. So we have here rho gh equals rho times omega squared r squared divided by 2. And so then we can move terms over and cancel, and we'll get this equation here. Oh, cancels. So that canceled, and then we really just moved the g down. And so we now have the height is equal to the angular frequency squared times your radial coordinate squared divided by 2 times the acceleration due to gravity. Now that we have this, we can then move forward on our next step. now that we have this equation that solves for height in this same situation, we're now going to see that there is this dip still in the volume of this fluid after the angular frequency is brought in. And so what you can see here is that none of the fluid has spilled over. So this volume here is going to be equivalent to this volume here. And if that weren't the case and some of the fluid were to spill over, this whole situation would not make sense. And so this is going to be somewhat difficult to find the volume for, but we know it's equal to this. So we have a cylinder, right? So it's pi r squared V equals pi, and then the radius r squared, and the height of this, which is labeled as the dip in this fluid. So it'll be d. So now that we have that, we want to find the volume for that and set them equal. So we'll blow this picture up right here. So that is blown up right here. And we'll have some differential radial coordinate here, r. Label that as dr. And then the radius from there to the other side. So there's just this radius r there. And there's some height of this fluid, h. So what we're doing is seeing how this volume changes with respect to your radial coordinates. So then change in volume is equal to h times 2 pi r dr. And so with this, we have this equation that we solved for earlier, and we will now plug it back in for h and then integrate. So what we have is dv equals 2 pi r and then times omega squared r squared over 2g dr. So then with this, we'll simplify and then integrate. And we'll have, pull out the constants first. So we'll have integral from 0 to v of dv equals, so then constants are 2 pi omega squared over 2g times the integral from 0 to big R, the radius of, and then r cubed dr. So then when integrating, we get this. We get v equals pi omega squared over g times r, big R, to the 4th over 4. So now this volume is right here, and that is the same as this volume right here, which we found for this. So we can then set this equal to that and solve it. So we'll have, or we're going to solve for this dip, this d that we labeled for the height of this fluid. Pi r squared d equals pi omega squared r to the 4th over 4g. So then when moving all this over, we'll get dip, d equals omega squared r squared. So that moves over, the pi's cancel, and then this is over 4g. So then now that we have this and this, we are getting closer to solving for our maximum angular frequency. So now that we have our dip, our value for our dip, and our height at any radial coordinate, we can then solve for our angular frequency. But first, we're going to solve for this h value here, this not volume, but rather the height of this cylindrical cup. So we have h is equal to, so we have this radius r, and we're going to subtract the dip, so we're now here, so minus d, and then plus this height at this radial position here. So now that we have this, we can plug in and then isolate to find our angular frequency. So we have h equals r minus our value for the dip, which is omega squared big R squared over 4g plus this height here, which is omega squared. And then this is a general term, so we have just small r, but for here we're now talking at the edge of the cup, so we're going to use big R instead of small r. This is r squared over 2g. So when combining these, and moving this over, we'll have h minus r is equal to omega squared r squared over 4g. So now we have this, and we can just isolate omega, the angular frequency, on one side and solve. So with that, we'll have omega squared equals 4g times the quantity of h minus r, and then divided by the radius squared. And so then with this, we can just take the square root of both sides and then have our angular frequency on one side. Omega equals 2 radical g h times the quantity of h minus r, and then over r. And so this is the final equation we want that solves for our angular frequency.